Hi everybody. So in our last video we were looking at Einstein's field equations in a little bit more depth, and we discovered the vacuum field equations, which are a particularly simple form that the field equations take whenever you are in a region of space where there is no mass. And in that case the field equations simply reduce to r mu nu equals 0, where here r mu nu is the Ricci tensor. And in this video now we're going to think about an extremely important solution to the vacuum field equations, and it's called the Schwarzschild solution, or the Schwarzschild metric. And what it's for is when your gravitational field is produced by a static, spherically symmetric mass. So for example, the gravitational field produced by a non-rotating star. Okay, like the sun. Now, in reality, the sun is rotating, but just as an approximation, let's just say that it doesn't, and see where we can go from there. And so remember, when we're solving the field equations, what we're looking for is a metric tensor. Okay, so remember, at the end of the day, what is r mu nu? It's the Ricci tensor. How was it defined? It's a contraction of the rank 4 curvature tensor. How is the curvature tensor defined? In terms of Christoffel symbols and their derivatives, and in turn, how are Christoffel symbols defined? The second way, at least method 2 of finding them, was in terms of derivatives of the metric tensor. So this is a second order differential equation for the 10 independent components of the metric tensor. Now, I am not going to go through here the full derivation, okay? So I'm going to just very, very briefly give you an overview of how this is done. So how you start with the vacuum field equations and get the final answer for the Schwarzschild metric. And there are some arguments required, but it turns out that the most general form of metric that is compatible with the spherical symmetry of the problem is as follows. So remember, you're looking for g mu nu, where mu nu can be 0, 1, 2, and 3. Okay, 4-dimensional space-time. But the most general metric that's compatible with the spherical symmetry of the problem is as follows. So G00 is just some function of r. G11 is just some other function of r. G22 is just r squared, and G33 is just r squared sine squared theta, where here we're choosing like spherical polar coordinates centered on the mass, basically, because of the spherical symmetry. So here x0, as always, is just ct, speed of light times time. x1 is r, x2 is theta, x3 is just an angle phi, and I'll use the different phi, so like the fancy phi here, because I use the other phi, just the circle with the line through it, I use that for gravitational potential. So at any rate, it turns out this is the most general form of solution for a spherically symmetric mass distribution. So it's diagonal, okay, and so f of r and g of r here are just unknown functions of r. Okay, so you can see here there's no dependence on time anywhere, because this mass is just static, it never changes. There's no dependence on angles here and here. So these f of r and g of r are just unknown functions of r. And then g22 and g33 are r squared and r squared sine squared theta, it turns out. But at any rate, what do you do to find the answers for f and g? And in other words, to solve the problem, to find the metric. And all the other elements are 0, by the way. So g mu nu is 0 if mu is not equal to nu. So the off-diagonal elements are all 0. But anyway, what you do is, here's your metric with these unknown functions. You can use them to find the Christoffel symbols. Okay, so use method 2 to take all the necessary derivatives, get all the Christoffel symbols. From there you can get all the elements of the rank 4 curvature tensor by taking the Christoffel symbols and their derivatives. And from the rank 4 curvature tensor you can contract the first and last indices to get all the 10 independent components of the Ricci tensor. And then by setting them all equal to 0 and solving, you will get the functions f and g, and you'll also need to use the requirement that far away from the mass, so in other words, for large values of r, everything should go back to Newtonian gravity. At any rate, here's what you find. I'm just going to tell you, f of r turns out to be 1 minus 2gm over c squared r, with a minus sign in front, in fact. And g of r turns out to be 1 minus 2gm over c squared r to the power of minus 1. Okay, so here g is the gravitational constant, m is the mass of the sun, or whatever the mass distribution is, c is the speed of light, r is just your distance out. Or well, not quite, r is not quite that, but just it's a radial-like coordinate, okay? So that's the answer, okay? So that's what the Schwarzschild metric is. So those will be the final answer for the components of the metric tensor that describe the curved space-time as a result of a static spherically symmetric mass of mass m. Usually, though, we don't write it this way. Usually we don't write all the components. We just write an expression for the line element instead. So usually what we write is ds squared is equal to minus 1 minus 2gm over c squared r times dx0 squared, which is c squared dt squared, plus 1 minus 2gm over c squared r to the minus 1 dr squared. Okay, so this is g00 times dx0 squared, g11 times dx1 squared, and then plus r squared d theta squared plus r squared sine squared theta d phi squared. So usually we will just write it like that. So that is the Schwarzschild metric. And so this describes the curved space-time that arises from the result of a static spherically symmetric mass m. The details of that, some of the details are in the notes in the PDF, not even the full details. It would take pages and pages and pages to go through all the full details of all those computations of Christoffel symbols and curvature tensor elements. But the outline of it is in the PDF notes, if you would choose to read it. You would never be asked in an exam or a test to actually prove the full thing. I mean, you would be there for days. But there it is. There's the answer. Now, what do we want to do with it? We want to find what happens then when I have a planet or some other object moving in the gravitational field of this mass m. So like the Earth moving in the gravitational field of the sun. What does the motion look like? Now we know in Newtonian mechanics what the answer is, hopefully. So if you remember your classical mechanics, remember that in Newtonian gravity, the gravitational force is a central force, and when that's the case, the motion of the particle will be a conic section. Okay, if you don't remember what a conic section is, have a look in the PDF notes. There are some details there, but a conic section, it's a special type of curve. Okay, there's the circle. Okay, that's the simplest type. There's an ellipse, a parabola, and a hyperbola. Okay, those are the four possibilities, although a circle is really a special type of ellipse, I suppose. But those are the possibilities. So, and in Newtonian mechanics, a planet in orbit around a star or whatever, it's one of those types. Okay, so it's an ellipse for a closed orbit, like the Earth around the Sun. In Newtonian mechanics, it's an ellipse. For an open orbit, so something that isn't actually bound, like perhaps you have a comet or something that comes in from far out, from deep space, and it comes close to the sun and goes off again. That trajectory is either a parabola or a hyperbola. In Newtonian mechanics, that is. What we want to see now is what happens in general relativity. So rather than using Newtonian gravity, what happens if we consider the motion of a particle, like a planet or a comet, in the Schwarzschild metric? Okay, so in the curved space-time described by the Schwarzschild metric, do we still get an ellipse and parabola and hyperbola, or do we get something else? We would hope that we don't get something too different. Okay, so all our observation for hundreds of years said, yeah, Newton's theory is right. That's what we thought, or near enough right. So whatever we get, from the Schwarzschild metric, it should be not a million miles away from what Newtonian gravity said, okay? So Newtonian gravity is not a bad approximation, so long as your gravitational field isn't too strong. So we should find something that's almost an ellipse, okay? So like for the orbit of the Earth around the Sun, we should hopefully find something that's almost like the ellipse you get in Newtonian mechanics. But let's see that in the next video.